In KYPipe, or any of our other analysis engines, we can enter demands. Demands are loads, or fixed flows, usually ones that are exiting the system. Or, said another way, they most often represent a constant loss of water from the pipes within the system. While physically they represent flow from pipes, mathematically their effect is assessed at nodes. In this model, we see that junction node J2 has a demand of 45 GPM. So 45 GPM exits the end of this pipe throughout the simulation. Whether that's an instantaneous loss for a steady-state simulation, or a loss over time for an extended period simulation, or a surge simulation. One thing we do not mean when we use the word demand is some kind of designated or enforced flow within a certain pipe. In this case, it happens that this pipe, pipe P2, has a flow that is equal to the demand at node J2, since this pipe is a dead end with no other devices. But the demand at this node is not limiting the flow within this pipe. For instance, if we connected this pipe to the rest of the system and then reanalyzed, we would see that the hydraulics of the rest of the system have an effect, and the flow within the pipe changes. In addition to representing a loss of water, demands can also be created that enter the system. By convention, we use a negative sign to tell the software that the demand is entering as opposed to leaving the pipe network. This example is a landfill gas collection model. Each landfill gas well is modeled as a node with an associated negative demand. Landfill gas wells are represented as negative demand nodes because they consist of flow-controlled inlets, and we can expect a steady flow rate at each wellhead. In this case, 60 standard cubic feet per minute per well. Once these demands enter the system, the cumulative flow is piped to this reservoir, representing the gas collection point. This also illustrates that demands are entered in the model's global flow units. The last example used GPM, but this model uses SCFM. Global flow units can be seen here in the System Data menu. As we've seen, demands are traditionally applied at junction nodes. Junctions are present at the end of pipes, whether at each end of continuous pipes, at the intersection of two or more pipes, or at the end of dead-end pipes. You can place one anywhere you need to within the model. There are two types of junction nodes, a regular or single-demand junction node and a multi-demand junction node. Looking at the node info window for each of these types, we see that the single demand junction node has a field for the amount of the demand and another for the demand type. The multi-demand node has fields for 5 different demand amounts and likewise 5 different demand types that all apply at the same point within the model. In other words, a junction multi-demand is like the single demand version, but with 5 slots instead of 1. It's important not to confuse the words demand type 1 in this row header with a type 1 demand. Rather, each pair of slots allows you to enter a demand amount and a demand type for that amount. The first pair could be type 1 demands, but, as shown in this example, they don't have to be. The total demand for the multi-demand node is summed at the bottom of the node info window. There is also a list of all demands, which are shown paired with their demand type, using colons as separators. The multi-demand junction node can be enabled from this menu if it's not already enabled. Creating a single multi-demand junction node makes all nodes in the model multi-demand nodes. So, what is a demand type? This is an integer value field that allows you to differentiate the source of different demands within your model. Type 0 always stands for residential demands. These types are sometimes shown in menus with a capital R as opposed to the numeral 0. The others start at type 1 and go up as integers from there, and their sources are user-defined. You can set them to represent any one of a number of different kinds of demands. So you might use type 1 to represent commercial, type 2 to represent light industrial, type 3 to represent heavy industrial, type 4 for agricultural demands, and type 5 might represent a specific business, such as a large manufacturing facility whose effect on the hydraulics of the system should be individually modeled. For instance, KYPipe was developed at the University of Kentucky, which is in Lexington, Kentucky. A few miles north of Lexington is Georgetown, Kentucky, where there is a Toyota manufacturing facility. This facility has large demands that follow their own diurnal demand curve based on 3 full shifts. So any model of the Georgetown area would consider this facility as its own demand, separate from the other demands within the city. This does bring up the question, why separate demands by type? The answer is that doing so allows us to use demand factors to alter the amount of demands entered into the model by type, as opposed to all at once. We'll discuss that more in Part B. Another way to define demands is using residential meters, each of which is normally used to represent an individual household connection, whether to a freestanding house, or to a condominium, or an apartment within a combined dwelling. Residential meters are part of a pipe, instead of being assigned to a node. Thus, they have no representation in the map area. We have to click on the pipe to see them. Looking at the pipe info window, we see this field, which allows you to enter a number of residential meters. This number could be a positive whole number or a fractional number. Pairing the number of residential meters with this field, which is a global value called the average residential meter demand, allows you to determine the total demand assigned to each pipe. As we saw earlier, this demand value will be in the global flow units of the model. We recently discussed demand type, and as you would expect, residential meters always have a demand type of 0 or R for residential demands. One important consideration is that while residential meters are assigned to a pipe, the flow is calculated at junction nodes since the software does not have a routine to draw flow into or out of the system directly from a pipe. If a pipe has 2 junction nodes at each end, the sum of the flow from all residential meters is distributed equally to those 2 junction nodes. If there is a device at one end of the pipe, such as a tank, an active valve, or a pump, and a junction node at the other end of the pipe, the entire demand will be attributed to the junction node. If there is a device at each end of the pipe, the software will give you a warning message saying that it cannot distribute the demands for the residential meters. If we want to know how many residential meters are assigned to each pipe in the model, we can see all of them, sorted by pipe, in Group Edit mode. We can also click the Complete Inventory button, which will show us the total of all residential meters in the model. The the last way to represent demands is with the metered connection. The main advantage of using a metered connection is that it allows you to couple the model to essential records, specifically utility customer records. A metered connection is what we call an internal node. That is, its icon is overlaid onto a pipe, but it is considered to be part of the pipe. It doesn't stop one pipe and start another. For that, you need a different type of node called an end node. So, since it is part of a pipe, in that way it is like a residential meter. Also like a residential meter, its flow is distributed to the junction nodes at either end of the pipe. But, unlike a residential meter, a metered connection node has a user-defined number of individual meters associated with it, which are connections with individual demands. These demands can be individually set by the user, whereas a residential meter is just one connection with an average demand. Here's how you enter data for a metered connection. This metered connection will be associated with an apartment building called the Gelnor Arms. The apartment building has 8 residences, each with a different daily demand, and these will be our individual meters. First, we'll right-click on a pipe and add a node, which will be our metered connection. Next, we'll click inside the Meters field to add individual meters to this node. The individual meters don't have a representation within the map area. We'll need to click on the metered connection node in order to see them. Alternately, there is a table of all individual meters. We'll talk about that in a minute. But to associate an individual meter with the metered connection node, within this menu, we'll click the button for Add a new meter. Next, we'll edit the individual meter. Normally, these have an alphanumeric code representing the account number of the individual utility customer. However you name them, you'll be using the description of the point where you take your company's monthly readings. As we said, each of these individual meters has a different demand. Normally, utility records contain the total volume for a certain time period, 1 month, or however often the meters are read, which you will need to convert to the model's flow units. We'll enter the demand type. Most often this will be residential, but you're not limited to one particular type, since, for example, you could have a mixed commercial and residential area you wanted to model using the same meter. The address is optional, but it's important to remember that the address represents the address of the individual meter, not the metered connection node. So in this case, it'll be the same street address for each meter, but a different apartment number. We would next repeat this procedure 7 more times to enter all the meters associated with this metered connection node. I said earlier that the demand associated with metered connection nodes is distributed to the junction nodes on either end of the pipe, and this is true. However, unlike residential meters, we account for the position of the metered connection node within the pipe, and the model weights the flow to either end of the pipe based on the node's differential location. In other words, for a metered connection node, which is 30% of the distance along the pipeline, 70% of its demands will be distributed to the closest node, and 30% to the farthest node. In this example, we see a metered connection with a total demand of 10 GPM. We can see that 8 GPM is going to this node, and 2 GPM is going to this node. However, if I drag the node along the pipe, and reanalyze, we see those demands change based on the weighting of the node's distance along the pipeline. In the Labels menu, we need to turn on Flow A, in order to see the total demand at each junction. We could turn on demands by checking this box, but that only shows us demands entered at junction nodes, not demands allocated from residential meters and metered connection nodes. Alternately, we can turn on result A for node labels and change the results from pressure to flow/demand, and we will see the total demand assigned to each node. We can group edit our metered connections to see them all at once. Their total number also appears if we run a complete inventory. As stated, there is a meter records table located here. As you add the data for each individual meter to any metered connection node, the data for the individual meter is recorded in this table. We see the meter number, again most commonly the account number, along with a demand type and the current demand amount. Each individual meter is linked to a node shown in this column. There's also a column for the address. You'll notice at the top that we have the option to save our meter record table's information. Creating a name here and pressing the Save button creates a text file with a .mtr extension. You can format your meter records the same way the text file is formatted, then copy your demands, or any other information, into the .mtr file, and then load it back into your .p2k modeling file in order to update your meter information. Next, we'll talk about demand factors. These are multipliers that affect the demands entered into the map area of the model. The demands entered thus far have probably been entered as baseline demands, but a demand factor can allow things like evaluating peak demand or slack demand, or really any variation desired by the user. For instance, a demand factor of 0.8 means the model uses 80% of the currently entered demand. And likewise, a demand factor of 2.2 means the model will use 220% of the currently entered demand. Demand factors are entered in the demand patterns table. Here we see there are two types of demand factors. The first is the global demand factor. As its name implies, it affects all demands entered in the map area regardless of type. So if I put a 2.0 in this field, all demands throughout the model are doubled, with one exception which we'll get to in a minute. In addition, below in the table, we can create demand factors that affect only certain types of demands, and which apply to different cases or times. So, what is a case versus a time? Cases are for steady-state simulations. When we open KYPipe, it is set up to analyze the current model in steady state. But if you want to look at different scenarios, say you want to start with a certain pump on and then turn it off, you would create two different steady-state scenarios within the same model. The first is called case 0, the baseline case, with the pump on, and next you create case 1 with the pump off. You can create more cases besides, dozens if needed. So, similar to turning a pump on and off, you can set up different cases which apply demand factors differently. You might start with case 0, which has all baseline demands. Then you might set up case 1 to triple the flow for all type 2 demands. Next, case 2 could halve the flow for type 2 demands. And case 3 might reduce all type 2 demands to 20% of the baseline. This gives you 4 scenarios in total including the baseline scenario. Here's what that would look like. We see the demands at this node changing as we use the slider to show the output for the 4 different scenarios. Notice none of these demand factors affect this node, which only has residential demands. Its flow is the same for all the scenarios. To change this, we would either have to set up demand factors in the residential row, or alter the global demand factor. Another thing to remember about this table is that any row which is blank is treated as if it contained the number 1, which of course leaves the baseline demands entered in the model unchanged for that demand type. Some simulations, however, require more than just a steady-state analysis. Therefore, KYPipe allows you to run extended period simulations, which are analyzed based on time as opposed to case. Here's the extended period simulation menu, with a checkbox to turn on the EPS, a total simulation time, and a simulation time step. The classic use of the extended period simulation is to watch tanks draining and filling, so the model is often set up by our users to run for either a 24-hour or 48-hour time period at a user-defined time step. Demand factors are also important for extended period simulations, although they are applied at certain times instead of cases. But either way they behave the same. They multiply the demands entered in the map area by demand type. Like running multiple steady-state scenarios, we can alter Type 1 demands using a set of demand factors. In this example, Type 1 demands are 70% higher at time equals 2 hours than they are at time equals 0 hours, and are 20% higher at time equals 10 hours. And residential demands are 20% lower at time equals 6 hours. There are 2 things to consider about the demand patterns table. The first is that the global demand factor and an individual demand factor can both apply at once. Thus, if we enter a global demand factor of 2.0 and a residential demand factor of 0.5, these will cancel each other, leaving the residential demand unchanged from what was entered in the map area. Second, be aware that a demand multiplier entered in the demand patterns table repeats unless changed. Thus, this value of 1.7 entered at time equals 2 hours in the extended period simulation is carried forward until time equals 10 hours, at which point it becomes 1.2, and that is carried forward for the remainder of the simulation, since there are no other data points entered. Likewise, the residential demand factor of 0.8 at time equals 6 hours is also carried forward. This means if you want to run a 48-hour simulation, you will need to copy the demand pattern out from the first 24-hour period into the second 24-hour period. The only exception is water quality and water age simulations, where this is not necessary. Those simulations rely upon the EPANet analysis engine, which automatically repeats 24-hour demand patterns when it finds that no data has been entered for the second 24-hour period, but the simulation is ongoing. There is no harm in copying the demands out, though, and we advise doing so in case you wish to switch back to a regular KYPipe style extended period simulation later on. There is one application that the demand patterns table is ideally suited for, which is diurnal demand patterns during an extended period simulation. For instance, we'll load the American Water Works Association demand pattern. It loads as a Type 1 demand. The model was set up this way because some users only use Type 1 demands by entering demands at Junction nodes, and Type 1 is the default. but I'm going to cut it from this row and paste it into the residential demands row. Since our examples thus far have also included residential meters, which always reference residential demands, and metered connections, which often represent residential demands, although they are not limited to any one type. If we were to copy this demand pattern into Excel and plot it, we'd see its diurnal character. Demands start low at midnight, have their first peak when people are waking up and going to work, followed by a midday lull, after which there's a second peak as people return from work, and this peak tails off again to repeat the pattern the next day. This line represents the average demand, so its factor is 1.0. It's important to note the meaning of the columns in this Excel file. This column, column 0, actually refers to the hour between midnight and 1 a.m. And column 1 refers to the hour between 1 a.m. and 2 a.m., etc. This explains why there are 24 entries in the demand patterns table per day, numbered 0 to 23, instead of being numbered 1 to 24. These columns can represent 24-hour time, also known as military time, or regular 12-hour/AM/PM time. If we were running different steady-state scenarios, as opposed to an extended period simulation, we wouldn't see column 0, since case 0 represents the baseline demands entered in the map area. Thus, the table would start at column 1, which would be our second scenario. Again, if you want this pattern to repeat for the next 24-hour period during a KYPipe simulation, as opposed to a water quality or water age simulation, you'll need to copy and paste it into the columns for the next 24-hour period, and so on for longer simulations. Last, I want to point out that we can save user-defined demand patterns and then open a new model and load them, so you don't have to keep entering a demand pattern that you want to use more than once. We can also clear out demand patterns, and we can check this box if we wish, which allows us to ignore the demand pattern, which means that only the global demand factor applies. So this summarizes the use of the demand patterns table for both steady-state and extended period simulations. However, there is one other place that demands can be entered, which is the node changes table. Here we can enter and edit demands at specific nodes at certain cases or times. In this example extended period simulation, we've created a demand that begins at node J4 at time equals 6 hours. While this change functions like any demand we might enter at the same node in the map area, there are two things that are different. First, it's not affected by any demand factors in the demand patterns table, including the global demand factor. Second, unlike data points entered in the demand patterns table, and unlike all other changes such as turning pumps on or off or changing valve settings, demand changes automatically time out at the start of the next case or time. They are not automatically carried forward past the next case or time. Therefore, this demand lasts until time equals 7 hours, that is to say, for a 1-hour period. If you wanted to maintain this demand for 4 hours, here's how that would look. We'll load a set of saved changes to show this. The node changes table was set up this way in order to allow operators to enter sudden demands, such as fire flows, without having to consider whether the fire flow would be affected by changes in the demand patterns table, and without having to enter a demand type. Incidentally, the node changes table could be used to enter sudden demands during surge simulations, and the same conventions would apply.